Welcome to today's problem walkthrough. We'll be exploring problem number 1415, titled the KTH lexicographical string of all happy strings of length n. In this session, we'll break down the problem, explore possible approaches, and work toward an efficient solution. Let's get started. In this problem, we are tasked with finding the KTH lexicographical string of all happy strings of a given length n. Now, what exactly is a happy string? A happy string is a sequence of characters that consists only of the lowercase letters A, B, and C, and it must not have any two consecutive characters that are the same. For example, UB or BAC would be happy strings, but AA or BBB would not because they repeat characters consecutively. Given two integers, n and k, the goal is to generate all possible happy strings of length n, order them lexicographically, and return the KTH string in this order. If k exceeds the total number of happy strings available, we return an empty string. To clarify, a string is considered lexicographically smaller if, at the first differing position, its character comes earlier in the English alphabet compared to the other string. Now let's look at some examples to understand this better. In the first example, the input is n equals 1 and k equals 3. For strings of length 1, the only happy strings possible are A, B, and C, because there are no consecutive characters to worry about. These strings, when ordered lexicographically, remain as A, B, C. The third string in this order is C, so the output will be C. This demonstrates how the KTH string corresponds to its position in the lexicographical order of all happy strings. In the second example, n is given as 3 and k is 9. Here, we are looking at happy strings of length 3. These strings include combinations like ABA, ABC, ACA, and so on, ensuring that no two consecutive characters are the same. When we order these strings lexicographically, the sequence becomes ABA, ABC, ACA, ACB, BAB, BID, CA, BCB, CAB, CAC. The ninth string in this sequence is CAB, so the output is CAB. This example shows how longer strings are generated while maintaining the happy string condition. In the final example, n is 2 and k is 7. For strings of length 2, the happy strings are FIB, AC, BA, BC, CA, CB. These are all possible strings of length 2 where no two consecutive characters are the same. However, there are only 6 strings in total. Since k is 7, which exceeds the total number of happy strings available, we return an empty string as the output. This highlights an important edge case. If k is greater than the number of happy strings that can be generated for a given n, the result must be an empty string. Additionally, when generating happy strings, we must always ensure that no two consecutive characters are identical, as this is a key requirement of the problem. To solve the problem of finding the KTH lexicographical happy string of length n, one approach we could consider is brute force. The idea here is to generate all possible strings of length n using the characters A, B, and C, and then filter out the ones that qualify as happy strings. Remember, a happy string is defined as having no two consecutive identical characters. Once we have all valid happy strings, we sort them lexicographically and simply return the KTH string. While this method is straightforward, the computational cost is significant. Generating all possible strings takes 3 to the power of n time, and the additional steps of filtering and sorting add further overhead. This results in a total complexity of 3 to the power of n plus m asterisk log m, where m is the number of valid happy strings. Moreover, the space requirement is also exponential, as we need to store all generated strings. Due to this inefficiency, especially for larger values of n, this approach is not practical for our needs. A more efficient alternative is to optimize the backtracking process by generating only valid happy strings directly. The key intuition here is that instead of generating all strings and filtering afterward, we can construct happy strings on the fly by ensuring that no two consecutive characters are the same during the generation process. This significantly reduces the computational burden. Using backtracking, we construct strings character by character, and at each step, we add only those characters that do not repeat the last character. We continue building until we generate the KTH lexicographical happy string, at which point we can stop. This method is much more efficient because it avoids unnecessary computations. Since each character in a happy string has at most 2 valid choices, the time complexity is reduced to approximately 2 to the power of n. The space complexity is also minimal, requiring only O(n) for the recursion stack. This approach strikes a good balance between efficiency and simplicity, making it a strong candidate. An even more efficient strategy is to use a direct mathematical construction, leveraging the combinatorial structure of happy strings. The insight here is that we can pre-compute the total number of happy strings of length n using the recursive property. Each valid string of length n1 can be extended by exactly 2 valid choices. With this, we can calculate the kth happy string without generating all the previous strings. The process involves sequentially deciding each character in the string based on the remaining count of strings. Starting with the total number of happy strings, we use the kth index to determine the position of each character and build the string step by step. This approach is highly efficient, with a time complexity of O(n), as we compute each character directly, and a constant space complexity of O(1). By bypassing both backtracking and sorting, this method is the fastest and most elegant solution for the problem. The chosen strategy is the direct mathematical construction approach, which stands out for its efficiency and elegance. The key realization here was that the problem could be reframed as a sequence generation problem under constraints, allowing us to directly compute the kth string using combinatorial counting. This eliminates the need to generate or store all happy strings, resulting in a time complexity of O(n) and constant space usage. Such efficiency makes this method particularly suitable for larger values of n and k, where the other approaches struggle with exponential growth. The main trade-off is that this approach requires a deeper understanding of the mathematical properties of happy strings, which adds some complexity to the implementation. However, the significant performance improvement justifies this added complexity, making it the ideal solution for the problem. To solve this problem, we need to generate the kth smallest happy string of a given length n. A happy string is defined as one made up of the characters of B and C, where no two adjacent characters are the same. Let's start with a straightforward brute force approach. First, we can generate all possible strings of length n using backtracking. This involves recursively building strings by appending characters while ensuring no two consecutive characters are identical. Once we've constructed all valid happy strings, we can sort them lexicographically and then simply return the kth string from the sorted list. This method ensures correctness, but it may not be the most efficient for larger values of n. Now, let's break the algorithm down further to understand it step by step. The constraints of the problem are critical here. We are limited to just 3 characters, and each new character must differ from the previous one. Using recursive backtracking, we can start with an empty string and build valid strings character by character. At each step, we check if the character we're about to add is the same as the last one. If it is, we skip that choice and move on to the next valid option. Once we establish the recursive backtracking process, the next step is the base case. When the length of the string reaches n, we know we've constructed a valid happy string, so we add it to our result list. After generating all possible happy strings, we sort the result list lexicographically. Given that there are only 3 characters in the alphabet, this sorting step is computationally inexpensive. Finally, we return the kth string from the sorted list. If k is larger than the number of valid strings generated, we simply return an empty string. Backtracking is particularly well suited to this problem because it allows us to systematically explore all valid combinations while pruning invalid options early. By ensuring each character added to the string satisfies the constraints, we avoid wasting computational effort on invalid strings. It's also important to note that the total number of happy strings of length n is limited to at most 3 times 2 raised to the power of n-1. This is because the first position has 3 choices, but every subsequent position has only 2 valid options. This keeps the search space manageable, even for moderately large values of n. Sorting is straightforward here, as the strings are already generated in a controlled manner, and the small size of the alphabet further simplifies the process. In terms of data structures, we use a result list to store all valid happy strings generated during the backtracking process. This list is essential for sorting and retrieving the kth string. Additionally, the recursive call stack acts as our mechanism for exploring all possible combinations of characters. To optimize this process, we can implement early pruning by skipping invalid character choices during generation. This significantly reduces unnecessary computations. Another optimization is to stop the backtracking process as soon as the kth happy string is found. By doing this, we avoid the overhead of generating and sorting all possible strings when only the kth result is needed. The pseudocode for this approach starts with a helper function for backtracking. This function takes the current string being constructed and the list of results as inputs. If the length of the current string matches n, we add it to the results and return. Otherwise, we iterate over the characters of b and c, checking that the new character doesn't match the last one in the current string before recursively continuing the process. The pseudocode continues by iterating through the characters and adding only those that meet the constraints. If a valid character is found, it's appended to the current string, and the backtracking function is called recursively with the updated string. Once all happy strings are generated, we sort the results lexicographically. After sorting, we check if k is within the bounds of the result list. If it is, we return the kth string. If not, we return an empty string. Analyzing the complexity of this approach, the time complexity is dominated by the backtracking process, which generates up to 2 to the power of n strings. This comes from the fact that there are 3 choices for the first character and 2 choices for each subsequent position. Sorting the strings adds an additional cost of m log m, where m is the number of generated strings. Therefore, the overall time complexity is 2 to the power of n plus m log m. For space complexity, the depth of the recursive call stack is n, and the result list stores up to 2 to the power of n strings, each of length n. This gives an overall space complexity of 2 to the power of n*n. Finally, let's address some edge cases. If k is larger than the total number of happy strings that can be generated, we simply return an empty string, as there is no valid kth string. For n equal to 1, the happy strings are just the single characters of b and c, unless k exceeds 3. When k equals 1, the first lexicographical string is directly returned without further computation. These edge cases highlight the importance of validating inputs and handling special scenarios to ensure robustness in the solution. With our algorithm and its optimizations, we can efficiently determine the kth happy string of any given length n, while keeping computational costs manageable and addressing all potential edge cases. This Python implementation solves the problem of finding the kth lexicographical happy string of length n. The solution uses backtracking to generate all valid happy strings. A nested backtrack function is defined to recursively construct strings, ensuring that the same character does not repeat consecutively. The current string keeps track of the in-progress happy string, and result stores all valid happy strings. Once all strings of length n are generated, the kth string, 1 indexed, is returned if it exists, otherwise, an empty string is returned. This approach ensures correctness and handles edge cases like k being out of bounds. This is the Java implementation of the solution for LeetCode problem number 1415, the kth lexicographical string of all happy strings of length n. The logic mirrors the Python implementation, using recursion to generate all possible happy strings of a given length and storing them in a list. Java-specific changes include the use of type declarations and the ArrayList class for managing the results. This code ensures happy strings are generated lexicographically and returns the kth string if it exists, or an empty string otherwise. To solve this problem, we start by understanding the key requirements. We need to generate all possible happy strings of length 3, which are strings made up of the characters of b and c where no 2 adjacent characters are the same. Once we have all these strings, we identify the 9th string in lexicographical order. The solution uses a recursive backtracking approach to systematically build these strings. Initially, we define a backtrack function with 2 inputs, current, which tracks the string being constructed, and result, which stores all valid happy strings. The process begins with an empty current string. At each step, we append one of the characters from the set, a, b, c, ensuring that it doesn't repeat the last character in current. For example, starting with an empty string, we append a, resulting in current equals a. Then, from a, we recursively try appending b and c to generate strings like a b and ac. These recursive steps continue until we reach strings of length 3, which are then added to the result list if they meet the criteria of being happy strings. This method ensures that all valid combinations are explored while avoiding consecutive duplicates. Once all valid happy strings of length 3 are generated, they are stored in the result list. For this example, the list contains the following strings in lexicographical order: ABA, ABC, ACA, ACB, BAB, BID, CUP, BCB, CAB, ECAC, CBA, CBC. Since we are looking for the 9th string, and the list is 1-indexed, the output will be CAB. Now, let's consider a different example where n is 2. Here, we follow the same recursive backtracking approach, but this time we generate strings of length 2. Starting with an empty current string, we append a B or C, and then recursively append the remaining characters. For instance, from current equals a, we can append B to form a or C to form AC. Similarly, starting with B or C, we explore all valid combinations while ensuring no two consecutive characters are the same. This systematic process ensures that all happy strings of length 2 are generated. After completing the recursive backtracking process for n equals 2, the result list contains the strings of AC, BA, BC, C, CB, arranged in lexicographical order. For this example, we are tasked with finding the 6th string. Since the list is 1-indexed, the 6th string is CB, which becomes our output. Let's now examine one more example where n equals 3 and k equals 15. In this case, we first need to determine if k is within the bounds of the total number of happy strings. For n equals 3, as verified in the previous example, the total number of happy strings is 12. Since k equals 15 exceeds this total, it is clear that there is no valid 15th string. As a result, the function returns an empty string. This demonstrates the importance of checking the bounds of k before attempting to retrieve a specific string from the generated results. The recursive backtracking approach ensures that all happy strings are generated systematically and in lexicographical order. This is because we iterate through the characters a, b, and c in a fixed sequence during the recursive steps. By maintaining this order, the result list naturally stores the strings in lexicographical order without requiring additional sorting. When retrieving the kth string, the only condition to check is whether k lies within the bounds of the result list. If k is valid, we directly return the string at the k1 index, given that the list is 0-indexed. Otherwise, we return an empty string. This systematic approach, combined with the simplicity of lexicographical generation and boundary checks, makes the solution efficient and easy to implement. To understand the time complexity of this solution, we start by analyzing the backtracking function, which is responsible for generating all possible happy strings of length n. A happy string must satisfy two conditions: no two adjacent characters can be the same, and the characters must be chosen from a, b, and c. At each position in the string, there are at most two valid choices for the next character, as the current character cannot repeat. This means that the total number of happy strings generated by the backtracking function is approximately 2 raised to the power of n, or 2 to the power of n. Once the base case of the recursion is reached, the generated string is added to the result list, which can hold up to 2 to the power of n strings. Finally, accessing the kth happy string from the result list is a constant time operation, O1. Together, these steps form the foundation of the time complexity analysis. Now, when we combine all of these steps, the time complexity of the solution is dominated by the backtracking process, leading to a final time complexity of O2 to the power of n. Shifting focus to space complexity, the recursive nature of the backtracking function means the recursion depth will be equal to the length of the string being generated, which is n. This contributes O(n) to the space complexity due to the call stack. Additionally, the result list stores all happy strings of length n. Since there are approximately 2 to the power of n such strings and each string has a length of n, the memory required for the result list is O2 to the power of n asterisk n. Combining these two factors, the overall space complexity of the solution is O2 to the power of n asterisk n. Let's compare this backtracking approach to a brute force solution. A brute force approach would generate all possible strings of length n, which amounts to 3 to the power of n strings, since there are 3 choices for each position. After generating these strings, it would filter out the ones that do not satisfy the happy string condition. This filtering step would require O3 to the power of n asterisk n time, as each string needs to be checked character by character. Clearly, this approach is much less efficient than backtracking, which avoids generating invalid strings in the first place. By ensuring that only valid strings are generated, the backtracking solution achieves a significantly better time complexity of O(2 to the power of n, making it a more optimized and effective approach. Examining the best, average, and worst case scenarios, we find that the time complexity remains consistent across all cases. In the best case, where k is very small, such as 1, the algorithm still generates all happy strings of length n before returning the first one. Similarly, in the worst case, if k exceeds the total number of happy strings, the function still generates all happy strings but returns an empty string. In both cases, the time complexity is O(2 to the power of n. The mathematical justification for this lies in the fact that there are always two valid choices at each position in the string, leading to a total of 2 to the power of n happy strings. The backtracking algorithm generates these strings efficiently without redundancy, ensuring the space complexity of O(2 to the power of n*n remains consistent as well. This uniformity across cases highlights the robustness of the algorithm. Here, we highlight some common mistakes and how to address them. First, one frequent issue is not handling consecutive characters properly. A happy string cannot have two adjacent characters that are the same, like AA or BB. This often happens when recursion or backtracking is used without checking the last character before appending the next one. To fix this, you need to explicitly validate the sequence as you build it. Next, inefficient string generation is another pitfall. Generating all possible strings of length n, including invalid ones, and then filtering them is computationally expensive, especially for large values of n. To solve this, adopt a pruning approach to ensure only valid strings are created during the generation process. Another common mistake is having incorrect base cases in recursion. If the base case is misconfigured, it can lead to infinite recursion or terminate too early, skipping valid solutions. Always ensure the stopping condition matches the required string length. Lastly, overlooking edge cases can cause problems. For example, small values of n like 1 or cases where k exceeds the total number of happy strings must be handled explicitly. Double-check edge cases and constraints to avoid such errors. Another challenge is efficiently handling large values of k. A naive approach, such as generating all happy strings and sorting them to find the kth string, can be incredibly slow for high values of k. Instead, leverage combinatorial counting to directly calculate the kth happy string without generating all strings. Now, from an interview perspective, this problem is an excellent opportunity to showcase your pattern recognition skills. It's a classic backtracking problem where you must generate sequences under certain constraints. Interviewers often look for your ability to recognize this pattern and design an efficient solution. Additionally, understanding the trade-offs between brute force and optimized approaches is key. While brute force implementations are easier to write, they don't scale well with large inputs. Using techniques like pruning or combinatorial methods demonstrates your ability to optimize for performance. Finally, focus on constraints. For instance, analyze the maximum possible values of n or k to determine the scalability of your solution. And don't forget to clearly explain your approach during interviews, especially how you minimize redundant computations with pruning strategies. This problem also connects to several related problems that help deepen your understanding of backtracking and constrained sequence generation. For example, LeetCode 22, generate parentheses, involves using backtracking to create valid sequences of parentheses under specific constraints. Similarly, LeetCode 46, permutations, challenges you to generate all possible permutations of a list, which is another classic backtracking problem. LeetCode 47, permutations 2, builds on this concept by introducing constraints to handle duplicates, making it an excellent practice for refining your backtracking skills. Of course, there's also LeetCode 1415, the problem we're discussing here, which requires generating happy strings in lexicographical order. Exploring these related problems will help you recognize patterns, improve your backtracking techniques, and strengthen your ability to handle constraints in sequence generation tasks. Now, let's explore some alternative approaches to solving this problem. First, recursive backtracking is a straightforward method where you build the string character by character, ensuring each step maintains the validity of the sequence. While simple to implement, this approach can become slow for large values of n or k unless you incorporate pruning to avoid unnecessary computations. Another option is iterative generation with pruning. Instead of recursion, you can use a stack or queue to iteratively generate valid strings while discarding invalid ones early. This avoids the overhead of recursive function calls but requires careful handling of constraints to ensure correctness. Finally, there's the combinatorial counting method. Here, you pre-compute the total number of happy strings of length n and use this information to directly determine the kth string without generating all possible strings. This approach is highly efficient but requires a solid understanding of mathematical insights and a meticulous implementation to avoid errors. Each of these methods has its trade-offs, so choosing the right one depends on the problem constraints and your familiarity with the techniques. Great job! Today, we tackled the KTH lexicographical happy string problem, summarizing key approaches and takeaways. Remember, mastering systematic generation of combinations and leveraging constraints is vital for solving such problems efficiently. Thanks for watching, be sure to like and subscribe, and I'll see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!